Good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course. Course ID is NOC 26 ME20, and it's a 12-week course. So we started with the basics of thermodynamics. Then we saw some fundamental equations. So we learned about compression waves, right? Then we moved on to these normal shock waves. So we learned its modeling, how normal shock waves are modeled using a piston example. Then this is week five's content. And the topic here is the broad topic is normal shock waves, its analysis. So, and the instructor for the course is Professor Niranjan Sahu from Mechanical Engineering IIT Guwahati, and I am a research scholar here at IIT Guwahati only. So there are two lectures in this week's content, lecture number 12 and lecture number 13. So we shall start this session in a couple of minutes. Let's wait to see if somebody joins. After that, we can start today's session. Thank you. Okay, so we can start with today's session, right? So there are two lectures, lecture number 12 and lecture number 13. So in the previous week's content, we had two lectures, lecture number 10 and lecture number 11. In lecture number 10, we saw the modeling of shock waves, how the compression waves coalesce and give rise to a shock wave. Then in lecture number 11, we saw properties change across a normal shock. Okay, so broadly this we have seen about normal shock waves. Then here we have two lectures. So first lecture is about inferences. Okay, in lecture number 12, we have some inferences. Then in lecture number 13, we see difference between isentropic compression and shock wave compression, because eventually shock wave is a kind of compression only. Okay. Then Hugonoid relations. So these are there in these two lectures. We shall see topics and questions. Okay. So we'll start with lecture number 12. So first we have limiting Mach number. So it talks about Mach number uh, across your normal shock. Okay. What is the limiting value of your Mach number? So lecture number 12, if you see. So first is your limiting Mach number. So if your Mach value is too high, okay, so in that case, your limiting value of M2, okay, is this. So this is for gamma equals to 1.4. So even if your Mach is too high, your M2 value will not fall beyond this. So this is the limiting value of your M2. Okay. Then, and formula for that is this. Under root of gamma minus 1 by 2 gamma. Okay. Then is limiting static property ratio. So limiting static property ratio. So this is there. So first is your limit M1 tends to infinity, rho 2 by rho 1 equals to, so this is this. So your static density ratios. So rho 2 by rho 1, its limiting value is gamma plus 1 by gamma minus 1. And for air, it comes out to be 6. Okay. Mach numbers limiting value is 0.378 and static density limiting value is 6. Then for your static pressure, this is infinite. So as your Mach upstream of your normal shock is increasing, so your static pressure ratio will reach infinity. Okay. Same is for your temperature also. Same is for your temperature, static temperature. Then third is entropy conditions. So if your entropy change is less than 0, it means the process cannot happen. Entropy change has to be greater than 0. Okay, greater than equal to 0. So this is your entropy change across a normal shock wave, right? So if your entropy change is positive, it means the process can happen. But in subsonic case, you will see that this entropy change is negative, which means your shock wave will not form in case of your subsonic flow, right? Then in your fourth inference, you see stagnation property ratios. Okay. So here, for your stagnation pressure, you have this formula. So across the normal shock, what happens to your stagnation pressure? So you have pressure loss. Okay, in your total pressure, your static pressure rises, but there is loss in total pressure, right? So this is about inferences. Then Krokow's theorem has been discussed. Now, what does your Krokow's theorem says? So it basically relates your fluid vorticity to your entropy change. So it relates your fluid vorticity with entropy change. So it basically says that if there is some change in entropy, in that case, your vorticity in fluid will be there, circulation, some type of circulation will be there. Okay, rotation, some kind of rotation will be there. And mathematically, it is written this way. This entropy change and enthalpy change, total enthalpy change. Okay, so this is your Krokow's theorem. Then gas property tables for normal shock relations. So this has been discussed. And there are numericals based on it. Okay. So these were topics related to lecture number 12. Limiting Mach number first was, which is under root of gamma minus 1 by 2 gamma. Then limiting static property ratio is there. Okay. So for your density, this ratio is 6 with air. Okay. For pressure and temperature, this goes to infinity. Then entropy conditions. So this has been discussed. After that, stagnation pressure ratios. So these have been discussed. Then Krokow's theorem has been discussed, which basically relates your entropy change with your fluid vorticity. Then we have questions. So let's see the questions one by one. So first question is this. please read the first question and try to answer this question. So first question is there. It says that all the flow properties undergo finite but very large change across the shock wave in dash manner. So based on options, let's see which one is the correct option. First is your isentropic. Second is your non-isentropic. Third is non-adiabatic. Fourth is none of the above. So if you see about entropy, if you pick up entropy, so what happens to entropy across a normal shock? Does it remain same? So we have seen here, so if you see this entropy conditions. So for your Mach greater than 1, your entropy is going to, for your supersonic flows, your entropy is going to increase across your normal shock, which essentially means that across your shock wave, the change is not isentropic. Isentropic means entropy is constant. So for your shock waves, this is not the case. Okay. In that case, B comes out to be the correct answer to this question. All right. Then moving on to next question. So now this says that question number 2, limit Mach number is a function of dash. So please try to give an answer to this question. Limiting Mach number is a function of. Is it a function of total pressure, total temperature, specific heat ratio, or none of the above? So if you see formula for limiting Mach number, this solely depends on your specific heat ratio gamma. Okay. So looking at the options, C option comes out to be the correct option, right? Then moving on to next question. So this data has been given for question number 3 to 6. This says that upstream of your normal shock, velocity is this, static pressure is this, static temperature is this, gamma is this, R is this. So this information has been given to us. Question number 3 to 6 given. V1 is 1500 meter per second. E1 is 13 kilopascal, that is this. Then temperature is 205 Kelvin. Gamma is 1.4. Then R is 287 joule per kg Kelvin. Now from your Rayleigh relation, okay. So here it says that stagnation pressure downstream of shock wave. So it asks for P02, stagnation pressure. Now we have this relation which is P1 by P01, sorry, P0 by P0, P1 by P02 is 2 gamma by gamma plus 1 m1 square minus gamma minus 1 by so this we have. But now in this relation we want m1. Gamma we have 1.4 given. So to find m1, so m1 is v1 by a1, right? Now A1 V1 we have, A1 we need to find out. So A1 is gamma RT1, which is 1.4 into 287 into 205. So if we work this out, this will come out to be 287 meter per second. Then, so your Mach becomes V1 by A1 equals to 1500 divided by 287. So if we calculate this, this will come out to be 5.23. So this is our Mach. Then, so P1 by P02 becomes, now I'll place values in this. So this would become 2 into 1.4 divided by 2.4 to 5.23 square, right? Minus 1.4 minus 1 divided by 2.4. This is your numerator. Minus 1. And your denominator is so this is your denominator. Now, if you calculate this, this will come out to be 0.028024. Your P1 by P02 will come out to be this. Then we need to find out P02. So this will become P1 by 0.028024. So P1 we have, if you see, P1 we have this 13,000 Pascal. So 13,000 divided by 0.028024. So this is your P02. Now if you calculate this, this comes out to be around 463888.09. Now if you divide it by 10 raised to power 6, you will get 0.46 megapascal. Okay, so this is your answer to question number 3. Then we have next question. Let's move on to next question. Find the stagnation temperature downstream of the shock. We need to find out T naught 2. So question number 4. Now we know that for normal shock waves, the total temperature remains same across the shock wave, right? And from isentropic relations, P naught 1 by T1 is equal to 1 plus gamma minus 1 by 2 M1 square. M1 we have 5.23, we have calculated this. Then for T naught 1, we can write T naught 2, right? And T1 we can take on the right hand side. Now we can place the values. So this we can do. Now if we calculate this, please calculate this. Let's see what the answer comes. So this comes out to be 1326.46 Kelvin. So this is your total temperature. If you have any doubt, you can just type in the comment box. I'll be happy to answer. So next question then we have, find the static pressure downstream of the shock. So P2 we need to find out. P naught 2 we have found out. T naught 2 we have found out. Now P2 we need to find out. So which relation should we be using to find out P2? So we need to find out P2. For this, we have this ratio that we have learned in previous week's content. So this is there. So this is there. Please calculate this. So this is 1 plus 30.745. Then, so P2 we need to find out. So P1 we have this. So calculate this. So if you calculate this, this will come out to be 412,685 pascals. That is, if you divide it by 10 raised to power 6, you will get the answer in megapascal. 0.41 megapascal. So this is your static pressure downstream of your shock wave. Then next question is there. So this asks for T2. Now to find out T2, which relation we will be using? So this is the relation that we are going to use. T2 by T1 is equal to 1 plus 2 gamma minus 1 by gamma plus 1 square into gamma m1 square plus 1 by m1 square into m1 square minus 1. So this is the relation that we are going to use. Now placing the values, this is 2 into 1.4 minus 1 divided by 1.4 plus 1 square into 1.4 into m1 is 5.23 square plus 1 divided by 5.23 square into 5.23 square minus 1. So this is this. This is 0.8 divided by 2.4 square into 1.4 into 5.23 square plus 1 divided by 3 square. One. Sorry. Now please calculate this. So this comes out to be 6.2538. Okay. Hence your T2 is 6.2538 into T1. Now what is your T1? So T1 is 205. So it will come out to be 1282.02 Kelvin. So this is your static temperature. Right? Okay then. Moving on to next question in that case. So this is the next question. So please read this question and try to answer this question. Then I'll discuss this. Okay, so this question says that when a flow field has a gradient of dash and dash, it is highly dash. So four options are there. The first option says that when there is gradient of pressure and entropy, so it is highly irrotational. So rotationality has been where it has been discussed that we need to recall. So second says that pressure and entropy, and third option is rotational. Sorry. Then third option says that enthalpy, pressure, and irrotational. Then your fourth option says that enthalpy, entropy, and rotational. So now I'll go back to Krokow's theorem. So what does your Krokow's theorem do? So if you see the mathematical expression of Krokow's theorem, so there is change in your enthalpy and then there is change in your entropy. And this is related to the rotationality of the flow, okay, across the shock wave. So looking at this, if we see our options, so if you see the D option, so we have enthalpy here also, we have entropy also. So there are gradients of enthalpy and entropy in the expression Krokow's theorem, theorem's expression, and which leads to rotational behavior of the flow. Okay, so this is question number 7. D is the correct answer to this question. So then We will take a short break of 5 to 10 minutes. After that, we'll be back and we'll continue with the session. Thank you. Okay, so we can continue with our session. So next question we have. So this question says that for a subsonic flow, entropy decreases across a normal shock, which is a possible situation. So this is what I was discussing, that entropy cannot decrease, okay? So if entropy is decreasing, this means that this situation cannot take place, okay? So in that case, this becomes a false statement, B option, right? So this is question number 8. Then we have next question. So this is from your lecture number 12 only. So we're just revising these numericals. So is standing normal shock. Now we know what is a standing normal shock, right? There are two types of shock waves. One is moving shock wave and one is standing, like we get in a wind tunnel. Okay. So standing normal shock in the test section of a supersonic wind tunnel has following upstream parameters. So Mach is given 3.5, static pressure is given this, static temperature is given this. Calculate the Mach number, static pressure, static temperature, and velocity downstream of wave. Also, we have given this table. This gas dynamics table has been given to us. For your 3.5 Mach number, you have P2 by P1, rho 2 by rho 1, T2 by T1. Okay. The ratio of static properties, this, then stagnation property. Okay, then P naught 2 by P1. So we have seen the formula for all these. Okay, then M2 is also there. So Mach, it says, now Mach is directly here, 0.4512. Okay. For static pressure, so we have been given P1 and P2 by P1 we can get from table, and then P2 we can get. Similarly, T2 by T1, T1 is given to us. T2 by T1 we can get from table, and further we can get T2. Then velocity downstream of wave. So velocity also can be managed. So let's see this question. So M1 is given to us as 3.5. P1 is given to us as 0.4 bar. right? P1 is given to us as minus 70 degrees Celsius, that is 203 Kelvin. So now M2 from table, M2 is 0.4512. Okay. Now E2 by P1 is given as this 14.12. 14.12, this is given. So P1 we have, P2 we can calculate. So please calculate this. So this will come out to be 5.648 bar. Okay, similarly, T2 by T1 is 3.315. Implies T2 is equal to 3.315 into T1, which is 3.315 into 203. So calculate this. So this comes out to be 672.94 Kelvin. Okay. Then pressure we have calculated, static temperature we have calculated, Mach we have, now velocity downstream of shock wave. From the definition of Mach number. So this we can write gamma is 1.4. This is 672.94. So calculate this. So this comes out to be 234 point. Meter per second. Any doubt in this question, you can type in the comment box. Okay. Zero point 0.4512. So this is 0.4512. Then 5.64. So this is there. Then next question is there. Let's see the next question. The blunt nose missile flies at Mach equals to 2.3. Calculate the pressure and temperature at the nose of the missile at sea level condition and at altitude of 18 km per second. So here also we need to calculate it, do this question using a table, gas dynamics table. But then also the information here that is, I believe, missing is that at 11 kilometers above sea level, we don't have the pressure and temperature. Okay. So this question has been plainly put, right? But if such type of question comes in exam, so how to calculate the pressure and temperature at 11 kilometers of altitude, this will also be given, right? So in our initial semesters, when we study aerospace engineering, so this we are taught this, okay? So how the pressure, how the temperature changes with altitude. So pressure and temperature has been asked. Yes. This is question number 10. So first of all, at sea level, we have T1 is equal to 1 bar and T1 is equal to 15 degrees Celsius. That is this. So maybe we can call it sea level, sea level. At 18 kilometers of altitude, T1 18, let's write it this way. This is this, and T1 18 is like this, right? Then for 2.3 Mach, some ratios have been given. So this ratio is not going to change, okay? So this is there. Now, because as per the question, we need to find out P02 and T02. Now, looking at the ratios, if you see, so we have P1, we don't have P01, but we have P1, right? And using this ratio, we can calculate P02. Now, if you see here, so this is the 7.294. So for MAC equals to 2.3, P02 by P1 is 7.294. Okay. So P02 at sea level will be equal to 7.294 into P1 at sea level. So this is 7.294 into P1. So P1 is 1 bar. So this will be 7.294 bar. Right? Then P02 at 18 kilometers, if you see, so this will be 7.294 into P1 at 18 kilometers. So this is 7.294 into 0.074 bars. So you see, as we are moving up in the altitude, okay, from sea level, so your pressure, static pressure decreases, correct? So if we calculate this, this will come out to be so this is 0.53 bar total pressure. Now regarding the total temperature, so for total temperature, first of all, because the total temperature does not change across the normal shock, so this is there. Then from isentropic relation, so this is there, right? So your T02 then becomes, for first of all, for sea level, we'll see T1 at sea level into 1 plus gamma minus 1 by 2 m1 square. So m is same. T1 is 288. 1 plus 0.4 by 2, 2.3 square. 2.3 only, I believe. Just 2.3 square. So if you work this out, this will come out to be 288 into 2.06 and 593.28 Kelvin. Now similarly, T02 at 18 kilometers altitude will be T1 at 18 kilometers altitude, gamma minus 1 by 2 m1 square. So this is going to remain same. This part is going to remain same. Okay. So only thing that is going to change is this T1. So this is 218. This is 218 into 2.06. So if you calculate this, so this will come out to be 449.08 Kelvin. So this is there. Then next question is there. This is 7.29 bar, 0.53 bar, 593.28 Kelvin, 449.08 Kelvin. So this is there. The next question is, a pitot probe inserted into supersonic flow field measured 3 bar pressure while static pressure in the flow field was. Calculate the Mach number at this point. What will be the entropy change across the flow field? So this has been asked. So P02 has been given to us. P1 has been given to us. Based on this, we can have this P02 by P1 ratio. And from here, we can estimate what will be our, what was our upstream Mach number, M1. Okay. Also using this, we can relate this ratio to P02. Okay. So from P02 by P01, we can get the entropy change because P02 by P01. Sorry, is there in your formula for entropy change. So so P naught 2 by P1. If we do this, so this is 3 by 0.4, which is 30 by 4. So this will come out to be around 7.5. Now, if you see here this table, so 7.5 for P naught 2 by P1 comes at this. Now, corresponding to this, we have this P naught 2 by P1, and MAC is this 2.35. Okay, so MAC is 2.35, and your P naught 2 by P naught 1 is this. Point 0.5615. Right. So here S2 minus change in entropy is minus R ln P naught 2 by P naught 1. R is 287 ln. If you calculate this, this will come out to be so this is your question number 11. 165.6 joule per kg Kelvin. Also 2.35 is your MAC. So this is your question number 11. Then moving on to thermodynamic lecture number 13, which is thermodynamic analysis of compression process. So here one graph has been drawn, lecture number 13. So this graph has been drawn for a polytropic process. Okay, polytropic process. So if your n is 0, what happens? How your graph looks like? This has been shown. If your n is 1, right? And if your n approaches to infinity, how your graph looks like. So this has been shown. Then Hugonoid relation has been discussed, which basically is this. So your internal energy has been linked to your pressure and density. So it is like this. Also, the ratio of your static pressures has been given. So this is specific volume. Okay, so this is there. Then one more topic has been discussed, which is isentropic compression versus your shock wave compression. So your shock wave compression is shown by Hugonoid curve. Okay. Then your isentropic curve is shown. Just give me a second. So if we see the graphs, so it is something like this. So this is your Hugonoid curve. This is your isentropic. curve. So now this is 1, this is 2. Now if we see the specific volume, okay, as the specific volume decreases, okay, so let's call it this point as 2 dash and this is 2. Now for Hugonoid curve, which is related to shock wave, and then isentropic curve, which is ideal case, we see that for same change in your specific volume. So if you see this, these 2 points, okay, A and B. The pressure change for your Hugonoid curve is higher in comparison to your ideal case. Okay, that is there. But in your shock compression, there will be entropy change. Okay, so this will be irreversible process, while the isentropic will be reversible. And also there will be pressure losses. There will be loss in the total pressure in the Hugonoid curve in comparison to your isentropic curve. So which states that your this Hugonoid curve, so this is less efficient in comparison to your isentropic change, right? So this is there. So this is it about your lecture number 13, right? Then there are 2 questions based on this lecture. So first is a polytropic process with n equals to 0 is known as dash process. So 4 options are there. So when n is equal to 0, if you see this graph, n is equal to 0 means your pressure is remaining constant. Pressure is remaining constant. To this process, what do we call? So we call it what? Isobaric process, right? Your pressure is remaining same. Then next question is the initial point on the Hugonoid curve corresponds to Mach wave. So true or false? This is true statement. Your initial point on the Hugonoid curve corresponds to a Mach wave, right? Weakest shock wave. So this is it about today's session. So I'll just conclude the session. There were 2 lectures, lecture number 12 and 13. So this was continuation of the previous week's content where we did modeling of shock waves, and then we saw properties change across the shock wave. Then after that, here in the normal shock wave analysis, what we saw is we saw inferences based on the previous discussions. And then we saw some limiting cases of the normal shock wave. So be it your Mach number or your static property ratios. Okay. Then one important theorem, Crocos theorem, we saw, which tells about the rotationality of the flow in case of entropy change and your enthalpy change, for which expression was introduced to us. Then in the next lecture, we saw Huguenot curve, and then how your shock wave compression is different from your isentropic compression. So these topics we covered and questions related to it. So this is about normal shock waves. From next week onwards, I believe, will be focusing on expansion waves and oblique shocks. So let's see that. Next session again will be on coming Tuesday from 6 to 8 p.m. Right? And next to next session, I am planning to prepone so that intimation you'll get through NPTEL only. So let's see. All right, then. Thank you. Thanks for watching this session. Bye.